I'll be speaking about the Arcus Explorer. And so what is Arcus going to do? Well, this is one of our promotional slides because one of the questions that you get when you're proposing a MIDEX in 2021 is, well, the decadal is about to come out. How do you know this is still going to be interesting science? And my answer is, well, it was interesting science in 2016, it was interesting science in 2010, and it was interesting science in 2001. And at that point, I stopped going back and looking at decadal reviews and annual reviews. Basically, this question of where the baryons are and how do they get there and where are they going next has been a live one for decades. And I suspect even if we knew the answers coming out of Arcus, we would still have new questions that we've been asking. So I don't have too many science slides in this talk because I was limiting it to just 5 minutes. But here's the basic picture, which should be familiar to all. And thanks to our very own Ben Oppenheimer for the simulation figure here. This gives you an idea of what Arcus's sensitivity is going to be like. I'll give you a hint, though, that whenever somebody is selling a promotional slide and shows spectra like this, they're likely showing the best case. And I will admit that I redid this simulation until this 3 milliangstrom feature actually just happened to show up quite nicely. It's actually there in a better case than it would be in normal. But the reality is that we will go down to 3 milliangstroms worth of equivalent width in oxygen 7, which is about a column density of 10 to the 15. And in the really dense cases, in the really deep cases where we're staring at a bright source for a very long time, I expect that we'll be able to get down to 1 milliangstrom. We're not really limited by background or other effects. It's mostly just the fact that the F values are small and the X-ray sources are not that bright. But that's the kind of numbers that we can get to. This would be, getting down to a milliangstrom would require on the order of half a megasecond to a megasecond on a fairly bright quasar. I would expect we do that, but keep in mind that a megasecond is about 3 weeks of time. So the other thing to point out is that all of these systems that we'll be surveying, and the Arcus science plan is a 2-year science observing plan, of which we'll spend roughly 3/4 of a year doing deep observations of AGN in order to look for the CGM around galaxies and clusters and groups. But all of those sightlines will, of course, go through the Milky Way. 6 of them go through M31, and they'll all go through the local group. So we will have the sensitivity to tell, for example, the difference in a velocity between the local group and the Milky Way, if there is one to detect, at the level of even 100 kilometers a second or so. So we'll get great probes of the Milky Way's halo. We'll do okay on M31, and we'll get a survey of, probably the plan is to have observations of about 30 to 35 sources, optimizing this in order to optimize the number of filaments you detect or galaxy halos you detect. Depends largely on the brightness, where they are, what galaxies are in the way. So it's a tricky proposition. But the plan is between 30 and 35 sight lines. We expect to get about 100 absorption features. And we might do a little bit better than that with longer observations. Actually, we will do better than that with longer observations. But the way that you have to play the game is that NASA requires you to put together a specific program for a specific number of years. And in Arcus's case, that's a 2-year program. And although we put most of our time into this, even 3/4 of a year, that's the numbers that you get. What does the instrument look like? Well, it's actually relatively simple. X-rays don't like to reflect very much. So in this case, we reflect from a 2-bounce system here, a Walter 1, here at the front, and then the X-rays go through what's called a critical angle transmission grating that I'll show in just a moment. They're diffracted. They pass through the 12-meter long focal length. This is a 10.85 meter boom that extends in order to give us the necessary focal path. And then lands on the detectors down here. These are standard X-ray CCDs of the kind that were used in Suzaku and a lot of other future missions. They're actually specifically the site that was used for Suzaku, but they're not wildly different from, say, the Chandra backside illuminated detectors. The key parameters are that the effective area, although it varies somewhat, will be greater than about 250 square centimeters. For comparison, right now, Chandra's HETG has a less than 1 square centimeter of area at oxygen 7. At launch, Chandra had less than 10 square centimeters of effective area at oxygen 7. So this is a huge leap forward from Chandra. The resolution, and again, at Chandra's resolution, when I say, for the 7 or 8 square centimeters that it had, was more like 700 or so, 750. We'll have a resolution greater than 3,000. Actually, our current best estimate is more like 4,000 or 4,500. But you have to put down requirements, and 3,000 we should be able to hit without any trouble at all. Can we build this? And the answer is yes. This is an actual picture of an X-ray optic of the kind that we're going to be using. This is what's called a silicon pore optic, and I could go into great detail about how they're made, but essentially this is a single crystal of silicon. There's no glue in there holding this together. It's held together by atomic forces. The X-rays go through and are focused. Now, this has been built, the technology has been developed by ESA for the Athena mission. Turns out that this same technology works beautifully for Arcus. Actually, ESA is continuing to develop the technology and make it better because it isn't quite yet what they want for Athena, but it has already exceeded what we require for Arcus. And so every improvement they make is just making our lives even easier. The X-rays then go through the transmission gratings. Here's a picture of the critical angle transmission grating. This is actually made by the same group at MIT that built the HETG gratings that are used on Chandra. The biggest difference is that these are now, in some sense, thicker gratings. They're actually about, the walls of the grating sides are about 10 times taller than the ones on Chandra. As a result, there's just more area to diffract with. The gratings are about 10 times more efficient than they are on Chandra, and they're done in blaze and they're read out at higher order. So the majority of our photons are read out in 5th, 6th, 7th order. That gives us higher resolution. That's where we get the 3,000 to 4,000 resolution that we're expecting. Does it actually work? Here's a picture and a beamline. Turns out ESA was doing some tests of some silicon pore optics. You can see them back here in the image. We asked, would you mind, after you're finished with your tests, if we could drop in some gratings in front of them and see how they work? ESA was amenable. So we did the test at the MPE Panther beamline site. And here you can see both the test results, the ray trace simulation, and the final result here. Now, in one of those things that should be a warning for the future, we know that this result shows that our resolution on the lab was greater than 5,000. But we don't actually know what the final resolution of the system is, because the limiting factor is that we don't know the atomic physics of the magnesium K alpha lines well enough in order to know what the natural line width should be. It's never been measured at this level. So one of the things we got to be careful about is that the atomic data that we need in order to do calibration and then understanding our data may not be up to what we really want with these new instruments. So to finish up, I know it's been a short 5 minutes here. We've got 3 science goals. The dominant one is looking at how baryons cycle in and out of galaxies. Now that's obviously stolen straight from the decadal phraseology, and I expect that we'll rephrase to whatever the decadal wants to call the problem of searching for hot halos in the next decade. But I'm certain it's going to be there. We'll also, of course, be looking at how black holes impact their surroundings. This will be looking primarily at the warm absorbers and also looking at stars and stellar systems. We are going to be 100 times more efficient, more sensitive than, for example, the Chandra HETG. So one of the things that we'll be doing, for example, is just surveys, short snapshot surveys of X-ray binaries and AGN to get a larger sample, which will be the equivalent of staring at existing systems for a megasecond with Chandra. So the amount of new material we expect to get from this is immense. And with that, I will finish up.